Okay, so we're starting here with our review of factoring. So this is going to be two parts. Both of them will be pretty short videos here. This first one, we have three objectives to talk about. So our first objective is to review GCFs and GCF factoring. We're looking for greatest common factors. The second objective we have is to take a look at factor by grouping. And our third objective is factoring trinomials. That are of the form ax squared plus bx plus c. Now, some of you may be thinking, hey, that's the quadratic formula thing, but no, we're not doing quadratic formula just yet. We'll be doing that in a later section. Now I'm going to throw up the fourth objective. This one is going to be split off from the other three, though, in the next video lecture, and that is factoring special trinomials. And we'll talk all about what the special trinomials are and how their factoring patterns look and how we factor those in the next video. But it's all one thing, reviewing factoring, and we're just splitting it up to not overwhelm ourselves. So let's talk about GCFs, or greatest common factors. So I could write up the definition for you, what a GCF is, but that's pretty boring and I imagine not something anyone wants to see. So instead, let's just take a look at a couple quick examples here to highlight greatest common factors. So let's say we were asked to find the GCF of 45 and 18. So we're looking for the greatest common factors, so that means we need to split our numbers into factors. Now, there's a couple ways you can do this. A lot of people tend to just do this as they get more practice by just kind of doing it in their head and guessing, and that's fine. So if you feel comfortable just factoring in your head and you can come up with the GCF, eventually that's all you're going to do. It's what I do. It's what most students do after a while. So that's fine if you can do that already. If you can't, don't worry about it. It's not a detriment to you. So let me show you how you would handle this if you're thinking, it's been quite kind of a long summer, a lot's been happening. I don't quite remember what to do to find GCF. So the way we do this is we just break this down into all the factors. So it doesn't matter how you start. So for 45, I know that 5 times 9 is 45. And then you look at, can I factor 5 anymore? Can I factor 9 anymore? 5's done, so I like to circle it to let me know that that's prime and we're done. So this is prime. And then 9, we know, can be split into 3 and 3. And then both 3's can't be split any further. So I'm going to circle those because those are prime. And so we can write 45 as 5 times 3 squared. And this is what's called the prime factorization. Factorization of 45. My word got a little big there as we kept going. And then we do the same thing for the other one. So 18, it doesn't matter how you start 18. So let's say 3 and 6. 3 is prime, so I'm going to circle that. 6 factors to 2 and 3, which are both prime. And so down here, I'm going to write 18 is 2 times 3 squared, because there are 2 3's just like there were 2 3's here. And so at this point, this is like I said, this is the long way to do GCFs. You don't necessarily need to do it this way. If you can just kind of think of it in your head, most people will. And if you're not quite there yet, you will get there as you do more practice with this. And so the idea is you're looking for what matches, and you cross out what doesn't match. And we see here that both have a 3 squared, and so that means 3 squared, which is 9, is our GCF. And that's how we handle finding GCFs the long way. So let's look at how we handle another one. So let's find the GCF, greatest common factor, 40, 100, and 360. So there is a trick to finding GCFs to make it faster initially, and you're looking at the size of your numbers. So I didn't use the trick in the first one here, number 1, but 40 is the smallest number. So that's going to be the limiting factor on all of these, because 40 only has so many different factors, whereas 100 is a lot bigger and 360 is even bigger than that. And so what you're looking at is you want to try and start with your smallest number. I didn't do that here, obviously. And see if you can figure it out from there. So 40, we know splits into 4 and 10. 10 splits into 2 and 2. 4 splits into 2 and 2, thank you. And 10 splits into 5 and 2. And all of these are prime. And so 40 is going to be 2 cubed times 5. So now we know, based on 40, because it's the smallest number, that there's only going to be 2's and possibly 1 5 in our GCF. Because if it's going to divide 100 and 360 and 40, all of them together, it's got to divide 40 first and foremost. And 40 is the smallest number, so it has the least number of things that divide into it. So the question is, does all of these things divide into either of these? So the next thing we do is we look at the next smallest one, which is 100, which we know is 10 times 10, 10 squared. And 10, of course, is 2 times 5. So 100 is 2 squared times 5 squared. So now, just like we did up here, we're looking for things that are in common. So we know there's not enough 2's in 100 to have all of the 2 to the third be a part of our GCF, and there's not enough 5's in 40. So my inclination right now is that my GCF is probably 2 squared times 5. So I'm going to write GCF equals with a question mark below it, because that's what I'm thinking here. Let's scoot this up. And again, just to kind of reiterate here, we're thinking about what the most in common numbers are in the prime factorizations of these. We have 3 2's in 40 and only 2 in 100, 2 2's. And so our GCF can only have 2 2's maximally. And in 40 we have 1 5, in 100 we have 2 5's, so that means our GCF can only have 1 5. So now when we go to factor 360, the same way we did, 360 I know multiplies 10 and 36. 10 is 2 and 5. 36 is 9 and 4. 9 is 3 and 3. 4 is 2 and 2. So if it divides into all three of these, 40, 100, and 360, it has to divide into this number here, 2 squared times 5, because that's what 40 and 100's GCF is. And so because 360 is bigger and has more prime factors than the others, 360 is, there are 3 of them, 3 2's, there are 2 3's, and 1 5. And so if we were to compare all 3 of these prime factorizations, again, we have to go with the smallest thing in common. Since these are both 3, but this is 2, our GCF does need to be 2 squared. Since there are no other 3's in either of these 2 factorizations, all of these will not count in our GCF. And then again, looking at our 5's, we have 1, 5 in each of these and 2 in here, but we can't take 2 because these are only 1. So our GCF is 20. Again, this is the long way. And so we can do this a little bit faster if we notice first that 360. So this is just a little bonus here. 360 is 40 times 9. That speeds things up. So anytime you have one of your numbers as a factor of one of the others that you're finding the GCF of, you can make it go a little bit faster because you know that this is not going to be a part of the GCF. So that's just a little trick. So let's look at a slightly more complicated one. This is 3, so let's find the GCF of 9x cubed and 3x squared. So we're going to use the same trick that we used a second ago. So when you're dealing with variables and GCFs, you treat your variables are treated like prime numbers. So you can imagine they're their own special primes. So x is x. It divides into x. The only other thing that divides into x is 1. So this is a special note we make sure we keep track of. So you can do this in 2 parts or you can do it all at once. It's not any faster one way or the other. So what I like to do is first I find the GCF of the constants or the coefficients. So the GCF of 9 and 3. And we can do that one fairly simple since there's a 3 there. That's going to be 3. And we find the GCF separately of x cubed and x squared. And again, we can do that one fairly quickly since x squared goes into x cubed exactly x squared times. And the reason for that is the numbers, the coefficients, are completely separate from our variables. They don't interact. Right? If you have 3x, it's 3 times x. It's never going to be something else. So then we take this piece and this piece together, and 3x squared multiplied becomes our answer. So you can go a little bit quicker on some of these things from this long process that we did here. Now the last example of GCFs is working into binomials and trinomials. So let's find the GCF of (3x to the 5th minus 15x). And our goal here is really not to just find the GCF, but we actually are going to use the GCF to factor. So this video and the next one, they are factoring sections, so it makes sense we should get to factoring. So the idea is what we do is we find the GCF of 3x to the 5th and 15x. So again, we're looking at the 3 and the 15 versus the x to the 5th and the x. And our GCF, 3 divides into 15. 3 times 5 is 15. So our GCF is going to have a 3. And x goes into x to the 5th. And so our GCF is going to be 3x. And then we can write this as 3x times 3x to the 5th over 3x minus 15x over 3x. So the idea here is we are multiplying on the outside, dividing on the inside, because our distributive property, if we were to distribute the 3x, we'll cancel these. And so we just simplify inside. So 3 divided by 3 is 1, which we don't need to write. X to the 5th divided by x is x to the 4th. Forgot the 3x on the outside. That's still there. 15 divided by 3 is 5. X divided by x is still just 1, so we don't need to write that. And so now we've factored it, and our final answer, 3x times x to the 4th minus 5. This is our standard, most common way of factoring, is looking for GCFs. You can think of this as your first line of defense. If you're not dividing, or if you're not finding GCFs first, it's going to make everything else a little bit more difficult the next couple sections, factoring techniques that we're going to be looking at. So let's move on to one of those techniques, and that is factoring by grouping. Factor by grouping. Okay, so the way that factor by grouping works, is a little review here, is we group 2 or more, sometimes more, terms together, and we factor using GCFs. Just like we did in the last example. So let's see what we mean by this. So let's say we're told to factor a particular expression, which is x squared y minus x squared minus 2y plus 2. So it's a big thing. It's not a trinomial. It's not a binomial. So what we do is we force a grouping, because our order of operations, if you remember, parentheses are just a grouping term. And so we can force parentheses in without changing too much or changing what it's equal to. So I'm going to group these two together with parentheses, and I'm going to group these two together with parentheses. Now notice the negative is on the outside, and I've changed that. So to make this the same, I need to adjust my positive to a negative sign, because that negative gets distributed, and it was negative 2y plus 2. So when I distribute the negative, negative 2y, negative negative makes a positive 2. So make sure when you are factoring by grouping, you put your parentheses inside a negative like this, that you remember to switch your signs. Excuse me. So now we can look at these individually, and they become just like the last problem that we just did. So here we're looking at the GCFs of x squared and y and x squared. And so we can factor out the x squared, because both of those have an x squared there. And so when I divide this term by x squared, I get a y. And when I divide this term by x squared, we get 1. And then over here, bringing down the minus, both of these have a 2, so I can factor a 2 out. When we divide this term by 2, we get y. And we divide this term by 2, we get 1 with a minus. And this is where you'll always know whether you've done your factor by grouping properly or not. Notice now we have the same binomial term sitting here, y minus 1 and y minus 1. So I can factor y minus 1 out of both of these now, because if we, for example, let's say y minus 1 equals w. So this is what's called making a dummy variable. So I'm going to swap in w for y minus 1 to w. And now we could factor that w out. Well, you don't need to do this step. This is kind of the justification step, and you don't ever need to write this actually. If you want to get the hang of it for a little bit, by all means, please do. but we can factor that w out, but that w is y minus 1, which means we can factor the y minus 1 out of both of these and pull this out all the way to the front, y minus 1. And when we divide this term by y minus 1, all that's left is an x squared. And when we divide this term by y minus 1, all that's left is this 2. And so now we've factored the blue thing that we started with into this nice compact form. Okay, so let's try another one real quick here. So let's look at factoring this expression, 3x minus 3y plus ax minus ay. So when you're just trying to decide when you're factor by grouping how to group your terms, there are always, not always, but there's going to be multiple ways we can do this. So a lot of people might look at this and say, I could factor by grouping up these two sets of terms. But, and we will do that over here. So I'm just going to rewrite this. Minus 3y plus ax minus ay. Sometimes we don't necessarily want to group up the terms that are right next to each other immediately. So I can move terms. So ignoring my parentheses I wrote in here, I'm going to move and switch these two terms, the negative 3y and the ax, and just swap them out for each other. So plus ax minus 3y minus ay. And I have the same stuff, right? Addition and subtraction are commutative. Remember, we can move them around. So then now if I group up here, I put the parentheses inside the negative, so we have to change this to positive. But I have two versions of the same problem. So let's go ahead and walk through solving each of these and see how this works. So over here, I can factor a 3 out of the first binomial. Dividing that, we have x. Dividing that, we have y. And on this one, I can factor an a. I have an a here. This is x. And then dividing that, we get a y again. We do our little double check. We have the same binomial term, x minus y, x minus y. That tells me I did it correctly. So then factoring the x minus y to the front, we have a 3 left over and a plus a left over. And that is fully factored. And so we're done on that side. And if we come over here to this version now, in this one, we're not factoring a 3 anymore. We're factoring the x. So we can pull the x out, and we get 3 plus a. Over here, minus stays, we can factor out the y, and we get the 3 plus a. And again, it's very different, but we have the same term here in our factorization, so we know we've done that right. So I can pull the 3 plus a out, and what's left is an x minus what's left here is a y. And these two things are the same. They're just written in different order, right? And you can do that because just like addition, multiplication is commutative, right? 3 times 2 is the same as 2 times 3. So this is our factor by grouping. Both of these are acceptable answers. The big thing to take away here is that you can rearrange your terms and it won't affect your answer. It does affect what you factor out. Notice here we factored out the x minus y, whereas here we factored out the 3 plus a. So just keep that in mind. If you're working with someone or you're checking work against someone else's work, know that the way that they factor by grouping might not be the same way that you factor by grouping, but if both of you have done it the same, you should get the same answer. They're just written in different orders. Okay, so the last thing for this video is our factoring trinomials, and then in the next lecture video, we'll be talking about the special trinomials. So this is our general factoring trinomials that are of the form ax squared plus bx plus c. So there's a couple things that we do here. The first is we always factor the GCFs. We want to make it that A, B, and C as simple as possible. So if we can factor, notice this doesn't have an x, so if we can factor a 2 out of A, B, and C, we want to do that first. And then what we look at is we look for the factors of A times C that add to B. So if that doesn't make sense, hopefully it will make a little bit more sense with some examples. So let's look at a few of those together. And this should take us to the end just a few minutes here. So number one, we're going to factor x squared plus 6x plus 8. So the first thing we do is look for GCFs. Now since there's no a term here, there's nothing to factor out of all of these. Even though 6 and 8 have a 2, this is a 1, a little invisible 1 here. So one thing I would recommend is you identify what the terms are. A is 1, B is 6, and C is 8, and there are no GCFs. Between 1, 6, and 8. So now we're going to do A times C, which is 8, 1 times 8, and we're looking at the factors of 8. So factors of 8 that add to 6. So there's a little bit of guesswork involved here, not too much, but the first thing you have to do is identify what are your factors of this number. So 8 is 2 times 4 or 1 times 8. And that's it. So those are the only two pairs that we could have, 2 and 4, 1 and 8. So we're looking for those factors to add to B. So you just check 2 plus 4 is 6, 1 plus 8 is 9. Well, B is 6, so it's not these, it's 2 and 4. And so another way that a lot of people are usually pretty familiar with is this, I think it's called the magic T or cross or something like that. There's different names. It's been called different things over the year. But you put your numbers here, and you want the numbers you choose here to multiply up to 8 and add to 6. And 2 and 4 do that. 2 times 8. 2 times 4 equals 8. 2 plus 4 equals 6. If you don't know what that is, don't worry about it. You don't need to force yourself to do it. So, since we have this, 2 plus 4 equals 6, the next thing we do is we take our x squared plus 6x plus 8, and we're going to split the 6x into 2x and 4x. Oops, plus 8. So by splitting this now, we can perform a factor by grouping. X squared plus 2x and 4x plus 8. We can pull an x out of this group and get x plus 2. And we can pull a 4 out of 4 and out of 8, and we get x plus 2. Again, I know I've done this correctly, so I got the x plus 2's popping up here. So then this becomes x plus 2 times x plus 4. And this is our factorization, our final answer. Now you may be looking at this and going, well, wait. This is 2 and 4, and the answer was x plus 2 and x plus 4. So there is a shortcut that you can jump from here straight to this. you do x plus whatever your numbers were. But this is only when a equals 1. So this shortcut only works. You can take your two factors that you figure out in this step and jump straight to this final answer when your first coefficient, your leading coefficient, is 1. If it's not 1, it doesn't work, and we need to split the middle term and factor by grouping. So let's take a look at two more examples, and then we shall be done. So yeah, I got some space here. So let's look at number 2. Will be to factor negative 5x squared minus 45x minus 70. So the first thing is to try and factor GCFs out of our coefficients. Now, we can pull a 5 out of all of these. Whenever you have a negative, you want to pull the negative out as well. It'll just make your life a little bit easier. So if I factor a negative 5 out, because our GCF is equal to negative 5, this will have an x squared left. Negative 45 divided by negative 5 will be positive 9. The x comes along. And negative 70 divided by negative 5 is positive 14. And so now we are factoring x squared plus 9x plus 14. So our a is 1, our b is 9, and our c is 14. And so now we kind of run through the same steps that we just did. Now, as you get more practice at this, you're going to get faster, and some of you may already feel confident enough and you know what the answer is. But again, you're looking at the factors of a times c, which is 14, and you want them to add up to b, which is 9. And so 14 is just 7 times 2, or 14 is 1 times 14. And so the factors, 1 plus 14 is 15, that's not 9, but 7 times 2 is 9. Now, since we have our a equal to 1, we can use the shortcut here. Remember that what we're really doing is taking the x squared plus 9x plus 14 and splitting that into x squared plus 7x plus 2x plus 14. And then we factor by group. But the shortcut is to just take our answers here, 7 and 2, and make this x plus 7 times x plus 2. Now, this is not the final answer because that negative 5 is still sitting there, so that needs to come along on the outside as well. And so this is our final factored version. And you can get there either using the shortcut, since our a is 1, or splitting it and factor by grouping. Notice here you'd pull out an x, and you'd have x plus 7. Here you'd pull a 2 to the outside, and you'd still get x plus 7. So our last example is usually the type of factorizations that students like the least. So we are going to factor 2x squared minus 5x plus 3. So the reason I say this is the ones that students typically don't like is because, one, the first thing to notice between 2, negative 5, and 3 is there are no GCFs. No GCFs. And we can't use the shortcut. Our a is no longer equal to 1. So a equals 2, b equals negative 5, and c equals 3. So then our AC that we multiply is 6. 6 can be 2 times 3. 6 can be 1 times 6. And this is where things get more complicated. Up until now, we haven't needed to think about this. But since our b is negative, we also have a bunch of negative factors. So 6 is also negative 1 times negative 6. and 6 is also negative 2 times negative 3. So if we want to add up to a negative, our factors are, one of them at least is going to have to be negative. So really, these two choices are not actually choices, because positive plus positive will always be positive. So we're really looking at negative 1, negative 6, or negative 2 and negative 3. And negative 1 plus negative 6 is negative 7, which doesn't work. So that one's out. And that leaves us negative 2 plus negative 3, which does work. So we take our 2x squared. We're going to split the negative 5x into negative 2x and negative 3x plus 3. And then we factor by grouping. Now, again, I put the parenthesis inside the negative here, so that means that we need to switch our sign inside here. So this needs to become a negative. And then we factor by grouping. So we can factor out a 2 from both of these and an x. So 2x leaves us with just 1x here and just 1 here. And over here we can factor out a 3. And that's going to leave it with an x, a minus, and a 1. And again, double checking ourselves, we have x minus 1 on both of these, so we know that that's correct. So factoring the x minus 1 all the way to the outside leaves us with 2x minus 3. And that is our final factored version. Now, I do know some people start to see the patterns easily enough, and they're able to sometimes in these types of trinomials jump from here straight to here, because you know you need a 2 for one of these x's to get 2x times x to make it 2x squared. I would recommend not doing that and just follow the method. The more you practice this method, the faster you get at it, the better you get at it, and eventually you'll be doing it without thinking. And when we get to the quadratics chapter, we'll be looking at both the quadratic formula and another method that allows us to factor and finish these a lot faster. But that's going to be the end of this first lecture. The next one that you'll be doing will be the special factoring techniques, special trinomials.